Okay, here's problem 347 in the problem solving videos. It says find V0 using nodal analysis, and we can see from our circuit that we have a dependent voltage source. Let's go through and identify the nodes for our circuit. We have a node here, 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 and then one big node across the bottom. So we have 4 nodes. And our problem solving strategy says select one as a reference. So let's select the bottom node as a reference. That way we can solve for V0 directly. So we have 4 nodes. That gives us 3 node voltages. And those node voltages are V1, V2, and V0. And I'll label those on the diagram. I'm going to call this one V1, this one V2, and that one V3. Remember the polarities of those node voltages. And then we're going to have to write 3 equations to solve for those 3 node voltages. Now, notice that our dependent voltage source is connected between 2 non-reference nodes. So we're going to have to use a supernode in this problem. And there's a supernode shown on the diagram. And let's start off and determine the constraint equation for that supernode. And remember, we're going to use KVL for that, and we're going to apply KVL around that loop to get the supernode equation. So if we do that, we'll have, starting here and going around clockwise, we'll have 4K Ix plus V2 minus V1 equal to 0. Okay, so then if we simplify that, we'll have V1 minus V2 is 4K Ix, and remember the K represents 1,000. Now, while we're working on the constraint equation, let's go ahead and express Ix in terms of the node voltages. And from our diagram here, Ix is V0 minus V2 over 2K. So now let's make that substitution. So we have V1 minus V2 is 4K times V0 minus V2 over 2K. And the K's canceling, we're left with a 2. So we have 2V0 minus 2V2. Now, let's move everything on the right hand side over the left hand side. And when we do that, we'll have V1 plus V2 minus 2V0 equal to 0. Okay, there's the first of our 3 equations, and that comes from the constraint equation. Now, we have to come up with 2 more equations, and now we're going to apply KCL at a couple of places. One is we're going to apply KCL out at this node, and then we'll apply KCL to the supernode. That'll give us our 3 equations. So KCL at this node, we'll have V0 over 1K plus V0 minus V2 over 2K is equal to 0.002. And again, we sum currents leaving through resistances and set that equal to the sum of currents entering from sources. And if we simplify this a little bit, we'll have minus 1 over 2K times V2 plus 1 over 1K plus 1 over 2K times V0 is equal to 0.002. So there is our second equation. And remember, we need 3. And what we're going to do to get that third equation is we're going to apply KCL to the supernode. And again, what I'm going to do is I'm going to sum currents leaving through resistances and set that equal to the sum of currents entering from sources. So KCL at the supernode yields the following. We'll have a current leaving here. That's V1 over 3K. A current leaving here. That's V2 over 6K. Then we have a current leaving the supernode there. That's V2 minus V0 over 2K. That's all the resistances. Then we have 8 milliamps entering, 2 milliamps leaving. Okay, so there's our equation. Now let's rearrange that and simplify it a little bit so we can be ready to solve it. So now we have 1 over 3K V1 plus 1 over 6K plus 1 over 2K times V2 minus 1 over 2K times V0 is equal to 0.006. And here is our third equation. Now, to solve those, let's put them in matrix form and solve them using MATLAB. And when we do that, so now we're going to write our equations in matrix form. Okay, and our first equation is that constraint equation. And you can see what it is. Here's our second equation. That, and then our third equation. And there our equations are in matrix form. Now, using MATLAB, here's our solution. V1 is minus 2.2857. V2 is 14.8571. And then V0 is 6.2857. So there's our answer.